Hello everyone, and welcome to the third video for Math 430 Abstract Algebra 1. In this video we're going to be talking about subgroups. And subgroups, basically from the name you can pretty much guess what they are. So if we have G be a group and let H be a subset of G, then if G is a group itself with the same operator as G, then we're going to say that H is called a subgroup of G. So subgroup is a group inside of another group. So it has all the properties of being a group. So in particular, the identity has to be a member of H. If we have two elements of H, then their product has to be in H. So that H has to be closed underneath the operator. And for everything in H, its inverse has to also be in H. The fact that G is a group with the operator means that the operator is already associative. So we don't really ever need to check associativity when we're checking with subgroups. But we do need that it has to have these other properties. It has to have the identity, it has to be closed, and it has to have inverses. So the common notation for subgroup, when notation is used, is typically the less than or equal sign. So you can kind of think about it as sort of being like subset but with a hard angle. So here are some examples of subgroups. Most of these we've already seen. So under addition, we saw that the integers and the rational numbers and the real numbers are all subgroups. And since the integers are inside the rational numbers, that makes it a subgroup of the rational numbers. Since the rational numbers are inside the real numbers, that makes it a subgroup of the real numbers. And the integers are also a subgroup of the real numbers. If we take for any integer n, we take all the integer multiples of that is going to be a subgroup of the integers. So in this notation, when I say n times z, I'm thinking about x times n for all integers x. So it's the set of all the multiples of n. So if you have x times n plus y times n, well then you end up with x plus y times n, and so that's still a multiple of n. So this means that we are closed. 0 is equal to 0 times n, and so it is an nz. So we have our identity, and if we have something x times n in here, then minus x times n is in here as well, and so we have our inverses. Okay, so it fulfills all the properties of being a group. If we take the subset that's just the identity itself of a group, then that is a subgroup. That is in fact the smallest subgroup, because subgroups, they have to be non-empty. You have to have an identity. You can't be, the empty set is not a subgroup because it does not have the identity. So just the identity by itself is going to be the smallest subgroup you can get. So let's just double check here. If I do the identity times the identity, I get the identity, and so that's enough for closure. The inverse of the identity is the identity, because if you multiply the identity by itself, you get back the identity. So it has its inverse, and it has the identity, so it has the identity. And so that gives you all the properties of a group. And so whenever we're thinking about subgroups, don't forget this important subgroup, this subgroup that we're going to call the trivial group. Last but not least, a group is always a subset. A set is always a subset of itself, and so a group is always a subgroup of itself. And so it is the group itself is always the largest subgroup of a group. So, for given some subset, how do we tell if it's a subgroup? Do we really have to go through and check all of the properties of the group? And the answer is not really. And so it turns out that really of all these things that we're checking, we really only need to check two. So if we let G be a group and let H be a non-empty subset of G, then it turns out that to show that H is a subgroup, we only need to check two things. So we need to check closure. And so that's property. That's one property. And we need to check that it has inverses. And if it's closed and it has inverses, then it's going to fulfill all the other properties of a group. So proof for this, we're just going to show that if it fulfills these two, then it's going to fulfill all the rest of them. So notice that we are saying that it satisfies closure, and so closure is a given condition. So it's done. Associativity is given from the fact that G is a group. Identities was given, or not identities, inverses is given as a condition. So we already have three of the four properties checked out. The last one just to check is that it has the identity. Well, since H is non-empty, there's something in H. So I can say let A be inside of H. So it has something in it. And then if it has something in it, then since H contains all the inverses of its elements, that means that A inverse is also in H. A inverse may be the same as A. It may not be the same thing as A. But we know that it's there. And so then by closure, A times its inverse is in H, and A times its inverse is the identity. And so we get that the identity is H. And so all four properties, if H has the property that it's closed under the operation and that it contains all the inverses of its elements, then it satisfies the other two properties of a group, and so that makes it a subgroup of G. So let's look at some examples using this two-step subgroup test. So we're going to let G be an abelian group under addition. So since we're talking about addition being our operator, we're going to say 0 is the identity. Then my claim is that if I take all of the elements such that when you add them to themselves, you get 0, so they are their own additive inverses, this is a subgroup of G. So let's work this out. So we need to show two things. First, we need to show closure. So let's let A and B be inside of H. And so then we want to think about, so in this case, since our operator is addition, we need to show that A plus B is in H as well. And so let's add A plus B to itself. Well, then by associativity, we can drop the parentheses, and I can rearrange, since it's an abelian group, it's commutative, I can rearrange that A and that B, and rearrange this to be A plus B. And then since A plus B are each in H, this is going to be 0 plus 0, which is 0. Okay, so this means that when we combine A and B, so in this case it's A plus B, we land back in H. So the subset is closed. Last but not least, for inverses, well, if A plus A equals 0, then that means that A is equal to its additive inverse. Right? We have found something that cancels off A, so based on the work that we did before in the last video, this means that A has to be its inverse. And so H contains its inverses. And we're done. So if we take a group G, and if we look at just the subset of the elements of G that commute with every other element, this subset is called the center. Okay, so when we write it Z of G, I think we use Z because in German center starts with a Z. And so Z of G is everything in the group such that AX is equal to XA for all X in G. Well, it turns out that the center is always a group. So let's prove that. So again, we're going to use the two-step subgroup test, so we need to show that it's closed. So let's let A and B be inside of the center. And then we need to show that its product is inside the center as well. Okay. Well, so how do we tell if the product is inside the center? Well, we need to multiply AB times anything else in G. So let's let X be in G, and let's look at AB times X. Well, since B is in the center, I can swap X and B. And so I have AXB. And so this is coming from the fact that B is in the center. And then from the fact that A is in the center, I can swap A and X. And so we end up with X times AB. So we have that AB times X is equal to X times AB. We're able to move AB to the other side of X and keep equality. And so this means that AB is in the center as well. And then lastly, we need to show that if A is in the center, then its inverse is also in the center. So if A commutes with everything, then its inverse also has to commute with everything. So let's do inverses. And we're going to use a little trick here. This is kind of a fairly common trick, or something like this is used quite often for proofs in algebra. So we're going to start with AX. It is equal to XA if A is in the center. And then on both sides of each equation, I'm going to multiply A inverse to the left and the right of both sides. And since AX is equal to XA, I can multiply A inverse to the left on both sides, and that doesn't change anything. And I can multiply A inverse on the right on both sides, and that doesn't change anything. So I'm going to do both. Then if you look at this, on the left-hand side, the A inverse and the A on the left, they cancel themselves out. On the right-hand side, the A times the A inverse on the right cancels themselves off. And so we're left with x times A inverse is equal to A inverse times x. And so this tells us that A inverse is inside the center. Right? So if we started with something, A is something in the center, x can be anything in the group, then using this trick, this shows that A inverse is also going to commute with x. And so since x is anything in the group, we're done. So in the last two examples, we've been showing that there's really, to show that a subset is a subgroup, we only need to check two things. And in fact, turns out that we can actually shorten that down and break it down to just one step on occasion to show that something's a subgroup. And so it turns out that if G is a group and H is a non-empty subset, then all we need to do is that if we take any A and B in H, we need to show that AB inverse is in H as well. Okay, and so why is this going to be true? Okay, so we're going to use that if this condition for any A and B implies that AB inverse is in H. So we're given that for any A and B in H, AB inverse is in H as well. And so we're going to use this to show that it satisfies all the properties of being a group. And so first, if H is not empty, so we have A is in H. And so in particular, since A is in H, H is not empty, so there has to be some A. Then by the above property, that means that A times A inverse is in H, and A times A inverse is the identity. So we have the identity. And then once we have the identity, going back to this rule again, well, I can use it as E, the identity, times the inverse of A is in H. And so the identity times the inverse of A means that A inverse is in H. And so it has inverses. And then last but not least, if B is some other element of H, well then by what we just did in the line above, this means that B inverse is in H. And so then we have that A times the inverse of B inverse is inside H. Well, what's the inverse of B inverse? Well, since we know that B times B inverse is the identity, that's the definition of B inverse of B inverse being the inverse. Well, since we saw that inverses are unique, this also means that the inverse of B inverse has to be B, because it's what we applied to B inverse to cancel B inverse out. And so we get that AB is inside H as well. And so we have closure. And we're done. So often, sometimes, this is the slick. Once you become a slick algebraist, you try and come up with one ways to show that subgroups or that subsets are subgroups using the one-step subgroup test. It doesn't always work out best. Often the two-step, even though you have to do two steps instead of one, it's often easier to do than the one-step subgroup test. But if you can figure out using the one-step subgroup test why something is a subgroup, it actually kind of it shows that you have a fair amount of understanding about what's going on with that subgroup. So that is all for this video. I will see you again soon.